Hello AP Statistics, it's Mr. Moon back again for the second stream of our heat day. And I just want to talk to you guys a little bit about normal distributions. So this is section 2.2. We're going to start with the A guided notes section of this PowerPoint. And this is going to replace the work we do in class today for section 2. So if you're section 1, we're going to get the chance to go over this, I think, tomorrow in class. But if you're in section 2, then I do recommend you watch this video so you're not missing out on the introduction. I'm going to try to keep this quick since a lot of the work we do with normal distributions we do on the calculator. We will discuss table A today, but I'm going to strongly recommend that you don't rely on table A for a lot of these calculations, and instead you learn how to do it on the calculator, which we're going to go over in class. So let's talk about normal distributions. We already talked about describing location. So after this section, ideally you should be able to describe and apply the empirical rule, the 68, 95, 99.7 rule. You should be able to describe the standard normal distribution. You should be able to perform normal distribution calculations, which is, I personally think, probably the highlight of this chapter. And you should be able to assess normality. So, normal curves are a specific type of density curves. Remember from last time that density curves have an area of 1 underneath them. And they are above the horizontal axis. So as you guys are going to see, the normal curve does meet both of those stipulations. And these normal curves are used to describe normal distributions. Some important notes here. All normal curves are symmetric, single-peaked, and bell-shaped. So when we talk about a normal curve, we're really talking about that bell curve shape. I think I said the other day that I really like that shape, right? This is a good shape for a distribution to have. It's really easy to work with. A specific normal curve is described by giving its mean, mu, and standard deviation, sigma. So you define a normal curve by these two numbers, and we'll look at what this looks like as we continue through the course. So here are two different normal curves. I want to be clear, these are not the standard normal curve. These are just two different normal curves. We'll talk about the standard normal distribution as we go. But note that each of these has a mean, mu, right in the middle of the data set because it's symmetric. They are both single-peaked, and they both have different versions of that bell shape. They also both have different standard deviations, denoted in both cases by that Greek letter sigma. Okay? So when we're talking about normal distributions, or normal curves, we really want to talk about the mean, mu, and the standard deviation, sigma. Okay? We want to get away from like x bar and s for these normal curves themselves. Okay, so a little more on normal distributions. Let's give a definition. A normal distribution is described by a normal density curve. Remember, we talked about on the last slide, any particular or specific normal distribution is completely specified by two numbers, which will be its mean, mu, and standard deviation, sigma. The mean of a normal distribution, that mu, is going to be the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side. If you've ever heard the word inflection point, that is what we're talking about. We can look at this more specifically in class, but this is where the curve actually changed from accelerating downward to accelerating upwards. You notice that I don't say moving upwards. I'm talking about accelerating upwards because it's still going down, but the curvature is now decelerating. I realize it's going to be confusing for some of you, especially if you haven't taken a physics course or a calculus course. We can talk about that in class, and I bet it will make a lot more sense. We abbreviate the normal distribution with mean mu and standard deviation as n, standing for normal, then parentheses, then you give the mean, comma, sigma. And that would be the actual standard deviation. So for example, you could say n parentheses 5, comma 3. You'd want to specify those numbers for each normal distribution you're talking about. Normal distributions are good descriptions for some distributions of real data. They are good approximations for the results of many kinds of chance outcomes. And many statistical inference procedures are based right on normal distributions. So it's helpful to understand what we're talking about, at least at a visual level, and hopefully at a deeper level. Okay? So, there are many normal curves. So we talked about how you need to specify the mean and the standard deviation for the one you're talking about. But they all have some properties in common. Here is probably the most important property of the normal curve, and this is called the empirical rule, also sometimes known as the 68, 95, 99.7 rule. And those are three numbers that you should have memorized in your head by the, end of certainly by the end of the course, probably by the end of this week or so. In the normal distribution with mean mu and standard deviation sigma, we see approximately 68% of the observations falling within 1 sigma of mu. That means that 68% of the data is within 1 standard deviation of the mean. About 95% of the data is within 2 standard deviations of the mean, and about 99.7% of the observations fall within 3 sigmas of the mean. So we're going to look at what this looks like on the graph below. Notice that between those two vertical lines that I just pointed to, there's 68% of the data in that one big hump. Now if we move out to still include the one big hump, but also include the lighter kind of aquamarine there, this is now going to include 95% of the data. You'll remember that I said in stats, we're often looking for something that has a 5% or lower chance of happening. Well, that means that that thing is probably going to fall 2 standard deviations or more out from the mean, because within 2 standard deviations is going to be 95% of the data. So, let's look at that last one. If we go out 3 standard deviations, this is now going to include a whopping 99.7% of the data. So almost all the data is falling within 3 standard deviations of the mean. And again, there are all those numbers together. So there's that middle 68%, there's that slightly wider 95%, and then there's that slightly wider, and that's 99.7% of the data. Okay, let's look at this distribution of Iowa Test of Basic Skills problem. The distribution is going to be n, so that's a normal curve, 6.84, that's the mean, 1.55, that's the standard deviation. So the first thing we want to do is sketch the normal density curve for this distribution. Remember, it should be symmetric, bell-shaped, and above the horizontal axis. Something like this would be fine. Note that the mean is right at 6.84. Note that the standard deviation goes out to the change in curvature point, which that looks roughly accurate, okay? And it should be going out about 1.55 in either direction. And what's beautiful about the graph that they've done is that they've actually labeled those points on the x-axis to be standard deviations. That's going to help us a lot in just a moment. So the next thing we need to determine is what percent of ITBS vocab scores are less than 3.74. So you will notice, if you look at the 3.74, that it is 2 standard deviations out. So about 95% of the scores are going to be within 2 standard deviations, which means 5% total will be outside 2 standard deviations, but that includes greater than or less than. In part B, the question only asks what percent blah 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 are less than 3.74 or less than 2 standard deviations out, which means we must be talking about only half of the 5%, so 2.5%. The next question says, what percent of the scores are between 5.29, that's 1 standard deviation down, and 9.94, which is 2 standard deviations up. This problem gets a little trickier. So what you have to do here is, we know we're including that central 68% of the scores, right? Now, we're also including half of the section outside the 68%, but inside the 95%. So the way we determine how much is in there, well, we take the 95 that should be covered by 2 standard deviations, we subtract the 68% that should be covered by that 1 standard deviation range, and we're left with, I think, 27. We divide that by 2. 13.5% of the data is going to be between +1 and +2 standard deviations. So we're going to add that 13.5%, which again is half that green zone on either side. Well, it's going to be that full green zone on the right side, but half the total that's within 2 standard deviations but outside 1 standard deviation. We're adding that 13.5 to the 68%, and I think we would get 81.5%. Okay, let's talk briefly about the standard normal distribution. So all normal distributions are the same if we measure in units of size sigma from the mean, mu as center. So the standard normal distribution is the normal distribution with mean 0 and standard deviation 1. And I want you guys to think of the standard normal distribution actually as the distribution of z-scores from any normal distribution. So what we're going to do down here, you will see that z-score formula again, okay? So if any variable x has any, if a variable x has any normal distribution n with a mean of mu and a standard deviation of sigma, then the standardized variable z equals x minus mu over sigma, which is just the z-score formula that we learned in the last chapter section, that is going to have a standard normal distribution. Remember, we talked about this very briefly in class, but the z-score should be centered at 0. 0 is going to be the z-score for our mean. So when we standardize this normal distribution, the mean should become 0. Remember, we're always dividing by sigma, so that sigma should become 1. That standard deviation should become 1. If you have a question about that, think about when we talked about transforming data. What happens when you divide by b? Well, the measures of spread also get divided by b. So when we take this z-score, we have to divide by sigma. So the measure of standard deviation, which is sigma, gets divided by sigma and becomes 1 for our new standard deviation of the standard normal distribution. This is tricky, but I want you to remember the standard normal distribution has a mean of 0 and a standard deviation of 1. If you can remember that, you're mostly good. You just also have to remember how to get there, but that comes with practice. Here's what it looks like. Mean at 0. 1 standard deviation out is 1. 2 out is 2. 3 out is 3. Hopefully not too hard to remember. Okay, because all normal distributions are the same when we standardize, we can find areas under any normal curve from a single table. This is called Table A. It is a table of areas under the standard normal curve. You will remember when we started talking about density curves that the area under the curve represents the proportion of observations or the probability of an outcome falling in that range. You're going to see in a moment that the table entry for each value z is the area under the curve to the left of z. That, among some other reasons, is the reason I do not like Table A all that much. If you have an Inspire, then there's a much easier way to do these calculations. If you have the TI-84, some of these calculations, I believe, by default, will go from the left to the z-score you give to find a probability. And we'll talk about how you can work with that in the calculator. Either way, whether you have the 84 or the Inspire, I will always recommend that you know how to use the calculator to do these calculations before you have to go to Table A. You really want to kind of avoid going to Table A unless you have to. It is quite a bit slower. Okay, so let's just forget that for a second, and let's say that we want to use Table A. We want to find the proportion of observations from the standard normal distribution that are less than 0.81. So what we do is you use Table A. We go down to 0.8, right? Z-score of 0.8. We go over to 0.01. They meet at 0.7910. If you imagine looking at this on the normal curve, the z-score is going to be positive, so the amount less than that should be bigger than an area of 0.5. The reason I say that is that if the z-score was 0, that would be the mean, but also the median, which means half the data should be below that. If we are at a z-score bigger than 0, and we're looking for points less than that, the area under the curve better be bigger than half, because 0 to the left of 0 was half. So 0.7910 makes some sense as an answer here, and that's really what you want to know. You want to be able to quickly check your answer like, okay, that makes some sense. Z less than 0.81 is going to yield an area bigger than half. Okay, so now we want to find the proportion of observations from the standard normal distribution that are between negative 1.25 and I suppose 0.81. It looks like that got cut off. So the area to the left of 0.81 is 0.7910. What you actually have to do is find the area to the left of z equals negative 1.25, again using Table A, and then you're going to subtract it. Now, the Inspire will let you do something called norm CDF, as will the TI-84. We're going to talk about both of these in class. They will simplify this work a lot because you can use norm CDF to find the total area between two z-scores. And in fact, you can even use norm CDF on any normal curve, not just the standard normal curve. So again, we're going to talk about that in class, but it is a very powerful tool to quickly find areas under the curve for normal distributions. Can you find the same proportion using a different approach is the question. I really need to reformat this slide. Yes, you can find the same proportion using a different approach. I suppose you could do that. That would work. I'm going to recommend that rather than going through Table A, that rather than doing all this work, you simply learn how to use norm CDF quite well, which we will go over in class and practice all year, and you'll get pretty good at this. So I'm going to pause here. I'm not going to show you how to do this stuff on the calculator today. I would recommend, if you want to learn how to use norm CDF, that you look it up, especially if you have the 84, where the mechanic is ever so slightly different. Just look it up on YouTube. How do I do norm CDF on the whatever calculator you're using? This video was for section 01. I apologize, I may have misstated that at the beginning. But this is for section 01. When I last saw you, we went over, what did we go over? Transforming data and density curves, and this was the video on normal curves. I am going to pause here. I am not going to go on to normal distribution calculations. We will get the chance to do that in class, so I'm not going to do that now. Please make sure you have looked over this video and completed your guided notes. You can just fill those out digitally. They are posted on the Google Classroom. And I will post this video as well to there. For now, though, this has been a great AP Stat stream. I know this one was quite early. Generally, when we have a snow day, just so you know, they will not be this early. I usually aim for about noon or 1, so that if you all want to join the stream, send questions through the chat, etc., I can generally answer those as we go. But for now, this has been good. This is Mr. Moon. I am signing off.